Hello everybody and welcome to our next webinar. Today we will speak about electrical capacitors simulation with QuickField. This slide shows analysis types available with QuickField. As you see, they include electromagnetic, heat transfer and stress analysis options. Electrical capacitors store energy in the form of electric field, so electrical models of QuickField are mostly commonly used for capacitor design and optimization. However, practical engineering often requires many other types of consideration. Thermal analysis may be helpful to estimate the capacitor stability at given operating conditions or maximum loads permitted. Magnetic analysis helps to evaluate the capacitor's inductance, and mechanical models may also be needed to estimate the mechanical stability of capacitor as an assembly, or at least to understand whether the detailed mechanical analysis is required or we are in the safe zone and there is no need for more complicated mechanical analysis. QuickField allows multiphysical analysis not only in the form of individual problems. It is also possible to link several problem setups featuring different physical fields defined on the same geometry. QuickField allows coupling. It is connecting of several types of analysis, for example, with results and then results of electromagnetic field analysis are used as input parameters for heat transfer simulations. Capacitor's design is often based on many thin layers of dielectric electrode composition. This may lead to large meshes of finite elements. Large meshes make the computational task very intense, and fast and efficient solvers of QuickField are of huge benefit. They are based on our special DDM procedure, which is abbreviation for domain decomposition method, and it provides extreme speeds. As you see on this slide, QuickField solvers feature quasi-linear dependency between the number of mesh nodes and solution time. And in conventional finite element packages, this dependence is of second order. Practically, it means what in majority of practical cases, QuickField gives results within minutes, not hours or days, which were traditional cost of finite element simulations before. In addition to graphical user interface, QuickField also features application programming interface, allowing access to internal functions and data structures from other Windows applications. This open object interface may be used from applications developed in many modern programming environments, which include Microsoft Visual Studio, then you may use C++ or C#, MS Office Visual Basic for applications, MATLAB, Python, Lua, and other programming environments. In some cases, QuickField components communicate with QuickField Core via this interface. This is how our parametric analysis utility label mover works. Open object interface to QuickField Core is called Active Field, and it includes objects and methods which are explained in detail on our website. We provide plenty of programming examples and free utilities you may use with any version of QuickField. And most important, all these diverse and sophisticated features are wrapped into the very straightforward, easy to use and intuitive user interface. No special training required. Even the high school students may start using QuickField for their class assignments in fully automatic mode, and gradually use more advanced settings and features and methods with growing complexity of their task. A range of QuickField applications is extremely large both in the types of analysis and level of problem complexity. Now my colleague will show how to use QuickField for capacitance simulations and for other types of analysis required for capacitor design.
Today we will review the following examples. The first case is the ideal and non-ideal capacitors. Then we will simulate the electrolytic capacitor and calculate the capacitance, the currents in the electrolyte, and the losses. Then we will calculate the capacitor inductance, simulate the capacitive displacement sensor, and take a closer look at the anode plate pitting technique that is used to enlarge the plate surface. And the last example is the variable capacitor. Now let's start with the test case. This is the cylindrical capacitor. It consists of two electrodes, the internal electrode, a positive one, and the external electrode. The inner electrode radius is 5 millimeters, and the outer electrode radius is 6 millimeters. The capacitance length is 40 millimeters. Our task is to calculate the capacitance. For this simple case, the capacitance can be calculated analytically. You can see the equation at the bottom of the screen. As you can see, the capacitance is a geometric parameter. It doesn't depend on the voltage applied. So what should we do to calculate the capacitance with QuickField? We should apply the voltage, the electric potentials to the electrodes, and measure the charge. Then the capacitance is equal to the ratio of the charge to the potential difference. Now let's start QuickField and simulate this case. I will create the new simulation case with QuickField. File, new problem. Here I specify the problem file's location and the project name. Then I should specify the field type, the problem type. To calculate the capacitance, I will use the electrostatics problem type. The other important parameter when you create a new problem is the model class. There are plane parallel, axisymmetric, and 3D extrusion model classes. For the capacitor, for the cylindrical capacitor, I will use the axisymmetric model class. Axisymmetric model class means that you have the rotational symmetry in your model. So you have draw on the upper half of the cross section. Now back to QuickField, and I will switch length units to millimeters. Now my problem is created. It's electrostatics problem, and I have to draw the geometry model. Now these are two electrodes of my capacitor. and there is some dielectric media inside. By the way, this equation is adopted for the ideal capacitor. In ideal capacitor, the field is concentrated inside the capacitor between the plates. There is no external field. So let's first simulate the ideal capacitor. In ideal capacitor, there is no external field, so only one block inside my capacitor. After the geometry model is ready, I should assign the labels to all geometric objects. I switch to select mode, click inside the block, and follow to the properties. Here I should type in the name of the block. I call it dielectric. And the name appears in the tree. I will give the name to the positive and negative plates. Now I have the dielectric media and I have the negative and the positive plates. The next step is to assign physical properties to each object. For the dielectric media, I should specify the electric permittivity. This is the A capacitor, so I specify the 1 for electric permittivity. For the plate carrying negative charge, I will specify zero potential. And for the positive plate, I will specify 1 volt potential, electric potential. Now I have the geometry model ready and the material properties and the field sources ready. The next important step is to build the finite element mesh. To do so, you should press this button. Now the mesh is ready. We can save all simulation files and start the simulation. Once the problem is solved, we can view the results. I will adjust the field picture, switch on the vectors, and zoom in so you can see better. On the screen you can see the equipotential lines and you can see the electric field stress vectors. In QuickField you can adjust the field presentation. Switch on and off equipotential lines, vectors, and the color map. This is the electric potential distribution shown in the color map. Now back to our task. We should calculate the capacitance. I know the potential difference. I specified the electric potential myself, but I don't know the charge. To measure the charge, I will build the integration contour. switch to the contour. I will surround one of the plates with contour and will calculate the electric charge integral. So this is the negative plates and the electric charge is negative. And if we divide the electric charge by the potential difference, and we will get the capacitance. The capacitance will be 12.3 picofarads. Let's compare these results. This result 12.3 with the analytical solution. The analytical solution gives me the 12.2. So there is a slight difference between the analytical result and the result we get in QuickField. Why there is such a difference? To solve the problem, QuickField uses finite element method. And the accuracy depends on the quality of the finite element mesh. Initially, QuickField builds denser mesh in smaller objects and the sparse mesh in larger objects. Then, after the problem is simulated, QuickField can automatically adjust mesh because on the initial step it doesn't know the field distribution, but after the results are calculated, QuickField can automatically adjust the mesh quality depending on the field distribution. So let's the problem again with automatic mesh refinement. I will perform only one step of the refinement. Now let's again adjust the field picture. And calculate the electric charge. Again, I will build the integration contour. And calculate the electric charge. Now, if I divide the charge by the potential difference 1 volt, I will get the capacitance. The capacitance is 12.20 and 6 picofarads. Let's compare this value with the analytical solution. 12.20 and 5 picofarads. Now you can see that you can trust QuickField results, and let's simulate the real capacitor. in real capacitor there is the air outside, and the field is not only concentrated inside the capacitor but also propagate outside. So I will add the air block in my model. That's it. This is the air block. I should give it the name. Air external. And I should specify physical properties for this block. Electric permittivity of 1. Now I will build the mesh and solve the problem. I will adjust the field picture and switch on the electric field stress sectors. You see, indeed, the field exists outside the capacitor. Let's calculate the capacitance of the real capacitor. Again, I will build the integration contour. And calculate the electrical charge. The charge is 12.72 picocoulombs and the capacitance is 12.72 picofarads. 12.72. And the capacitance of ideal capacitor is 12.20. You can see there is a difference between the ideal and real capacitor, and QuickField allows you to simulate both ideal and real capacitor. Now let's move to the next example. This is the electrolytic capacitor. The capacitor consists of cathode foil with negative potential, the anode foil with positive potential, electrolyte between the cathode and anode foil, and it's often the case that the anode foil is perforated to increase the foil surface. We know that the capacitance depends on the surface area. Cathode is the conductor, electrolyte is the conductor, anode is the conductor. So where is the dielectric? The anode foil is covered with the very thin layer of the oxide. The anode film thickness is about 100 microns and the oxide film thickness is only 1 micrometer. But first we will simulate the simple case with smooth anode foil without perforation. We'll simulate this small area. So this is the small piece of my electrolytic capacitor. I have the anode foil, the oxide layer, the electrolyte, and the cathode foil. And my task is to calculate the electric capacitance. Anode, cathode, and electrolyte are conductors, so the electric field is concentrated only in the thin layer of the oxide. To calculate the capacitance, I should assign some electric potential to the anode foil, to the cathode foil, and calculate the electric charge. So let's start QuickField and take a look at this case. And this is the electrolytic capacitor simulation case. Let me show you the problem properties. This is the electrostatic problem. I will use this case to calculate the capacitance. The model class is plane parallel. This means that I will simulate the cross-section, and the cross-section remains the same along the z-axis. I have only the small piece of my capacitor. The z-length of this piece is only 100 micrometers. And naturally I choose the micrometers as the length units. Now let's take a look at the geometry model. Here I have 4 objects: the anode foil, the cathode foil, electrolyte, and the oxide film. You know, there is no electrostatic field inside the conductors, so I will not simulate the conductors block here. The only block with properties, with physical properties, is the oxide film. For the oxide film, I specify the electric permittivity of the oxide. It's 10. And the electric potential is conducted by the coil, by the foil conducted by the electrolyte, and the electric potential drop appears on the oxide film only. So on the one side, on the anode side, I specify positive voltage 1 volt, and on the cathode side I specify 0 voltage. Now let's take a look at the simulation results. I will adjust the field picture so you could see better. Again, we simulate only the small piece of the capacitor, so there are no side effects here, as we take this piece from somewhere in the middle of the capacitor. Now back to our task, we need to calculate the electric capacitance. I know the potential difference as I specify the electric potential of the both anode and cathode foils, and I need to calculate the electric charge. Again, to calculate the electric charge, I build the integration contour. I surround one of the plates follow to the integrals and calculate the electric charge. (8.85 times 10 to the power of minus 13 coulombs. And if I divide the electric charge by the potential difference, I will get the capacitance. Please note that this charge is accumulated by the small piece of the capacitor foil. Let's calculate the capacitance per the 1 square meter of the foil area. So I will build the new contour, select the one of the foil and calculate the surface area. 10,000 square micrometers. I'll better switch to the meters. (10 to the power of minus 8 square meters). So let's calculate the capacitance. 8.85 times 10 to the power of minus 13 divided by the 10 to the power of minus 8. It is 1, 2, 3, 88 microfarads per square meter. 88 microfarads per square meter of the anode foil. Now, if you know the foil area, you can calculate the capacitance of the real capacitor. Now let's move to the next task. Our next task is to calculate the electric current and the power losses in the capacitor. Again, this is the same small piece of the electrolytic capacitor. We already calculated the capacitance, which is 88 microfarads per square meter. The capacitor works at the frequency of 20 kilohertz, and the voltage applied is 40 volts. Where do the losses appear in the capacitor? The current flows first in the foil, then it's a conducting current, then it's transferred to the displacement current in the oxide field, and then again it's a conducting current in the electrolyte, and the electrolyte has very low electric conductivity compared to the aluminum foil. And what will be the current value? I know the capacitance, I know the voltage applied, and I know the rotation frequency, angular frequency. Let's calculate the current density that will flow in the electrolyte. So this is the capacitance in farads per square meter. Times to the times to the 2 p and 20 kilohertz. So this is the current density that will flow in the electrolyte, 445 amperes per meter. Now we know the current density and calculate the volume losses. Let's simulate this case in QuickField and calculate the losses and the current distribution. This is the QuickField and the new simulation problem. Let me show you the problem properties. You can see this is the AC conduction problem, as I will not calculate the capacitance, but I will calculate the current distribution, current flowing in the electrolyte. For this problem, I specified their frequency 20 kilohertz. The length units are micrometers, and again this is only the small piece of the capacitor, 100 micrometers by 100 micrometers. Let's take a look at the geometry model. You can see this is the same geometry model. The green is the finite element mesh. The finite element mesh is constructed of triangles. Now what I have here in the geometry model? Again, I have 4 objects. I have the anode foil, and for this foil I specify the electric conductivity of the aluminum. I have the cathode foil, and for this foil I also specify the electric conductivity of the aluminum. And I have the electrolyte. I know the electric permittivity of the electrolyte, and I know the electric conductivity of electrolyte. So I have specified both values here. And I have positive potential applied to the anode foil. Here I specify the current density. The normal current density that will flow in my capacitor. And the cathode foil has 0 voltage potential. One foil, another foil, electrolyte, incoming current density, and the 0 potential. Now let's take a look at the simulation result. Again, here you can see the electric field equipotential lines. Let's adjust the field picture. I will switch on the color map of the electric potential and the vectors of the current density. Here you can see how the current flows in the electrolytic capacitor. You can see there is almost no voltage drop in the anode foil, and there is no voltage drop in the cathode foil, but there is some slight voltage drop in the electrolyte. Now let's adjust the field picture again and switch on the color map of the active power losses. There is virtually no losses in the foil, in the metal foil, and all losses are concentrated in the electrolyte. Let's calculate the losses value. I will build the integration contour simply clicking inside the block and choose the integral value. Active power produced in the volume. And this is the average power produced in the volume. 9.8 times 10 to the power of minus 9 watts. Remember, this is only the small piece of the capacitor. And this volume is 500,000 microns cubed. I will switch to the meters. 5 times 10 to the power of minus 13 meters cube. Again, let's calculate the power in watts per meter cube. Let's calculate the power density. So the power is 9.8 times 10 to the power of minus 9, and I divide the power value by the volume menu. Now you've got it. This is the power losses, 19,000 watts per 1 meter cube. Almost 20 kilowatts per 1 meter cube. And as I know the power losses, I would be interested in calculating the temperature. So our next case is the temperature calculation in the electrolytic capacitor. The electrolytic capacitor consists of the container, the steel terminal, there is the air outside, and inside there is the mix of electrolyte, the foil, the insulation. I know the power losses produced in the volume. (9,700 watts per meter cube). I know the electrolyte thermal conductivity. It's 5, and I know the aluminum container thermal conductivity. It's 200. And the conductor is cooled the natural way by the air flowing outside. I know the convection coefficient, it's 12. We know the losses, we know the material properties. Now let's calculate the temperature distribution. I'll start QuickField, and this is the problem to calculate the temperature distribution. Let's take a look at the problem properties. Naturally, it's the steady state, the heat transfer problem. To calculate the temperature distribution, I need the heat transfer problem. And the model class is axisymmetric. Axisymmetric means that we have the rotational symmetry. And in my model, only the upper half of the cross-section present. Let's take a look at the geometry model. I have 3 blocks here. The container, and for the container I should specify the thermal properties, the thermal conductivity of the aluminum. It's 200. There are no power losses in the container. I have the electrolyte. I specify the electric conductivity of electrolyte, and I specify the volume power losses. And I have the terminal, and for terminal I specify the thermal conductivity of steel. And the convection outside on the external boundary of the capacitor, I specify the convection condition. The convection coefficient is 12, and the external temperature is 20 degrees. I have to specify in Kelvin degrees, in kelvins, so I type in the formula 273 plus 20. Now let's take a look at the simulation results. Here you can see the field distribution inside the capacitor. And the most heated point is here. And it has the temperature of 305 kelvins. It's 32 Celsius degrees. So this is the way how you can calculate the temperature distribution in the capacitor. Now let's move to the next problem. The capacitor inductance. In some application at high frequency or when the transient voltage process appears, the capacitance inductance plays some significant role. So we should, in this case, we should calculate the inductance of the capacitor. The capacitor consists of two foils. If we unfold the capacitor, we will see this as two parallel conductors. One conductor carries current in one direction and another conductor in another direction. This is the anode plate, this is the cathode plate. The length of the plates is 2 meters and the thickness is 20 millimeters, and the distance between plates is only 1/10 of the millimeter. Our task is to calculate the inductance. Let's take a look at these plates from the left side. I will start QuickField and show you what you will see if you look at the plates from the left side. This is what you will see. You will see positive plate with direct current and the negative plate with back current, and some insulation between plates. To calculate the inductance, I will use the magnetostatic problem. The model class is plane parallel, as I have the same cross section along the foil. The model depth is 2 meters. And this is the plate, and the plate length is 20 millimeters. And the distance between plates is 1/10 of the millimeter. In magnetic problem for all materials I should specify the magnetic properties. For the air I specify the magnetic permeability of air, and for the plate I specify the current. The plate now is simulated is the very thin layer, so I specify the layer current density, linear current density. Ampere per meter. Negative current for the negative plate, positive current for the positive plate. Now let's take a look at the simulation result. This is the magnetic field produced by the capacitor. I will zoom in so you will see better and switch on the flux density vectors. And I will switch off the magnetic field lines. Here is the magnetic flux produced by the capacitor. And how should we calculate the inductance? The inductance is the ratio of the magnetic flux to the current that produced this flux. I know the current. I specified it myself, and I need to calculate the flux. I see the flux, how the flux flows in my capacitor. And to calculate the flux, I simply put the contour here across the flux path and calculate, and I will calculate all the flux that will pass my contour. This is the magnetic flux value. And if I divide the flux value by the current, I will calculate the inductance. The other option is to use the built-in inductance wizard. There are two options to use the flux value and the current, or to calculate the inductance through the stored magnetic field energy. I will use the stored magnetic field energy approach. So this is the energy stored by the magnetic field, magnetic energy stored by the capacitor. And this is the current flowing. Now this is the value of the inductance, 1.2 times 10 to the power of minus 8. Or, if we recalculate it, this is 12 nanohenry. Very small value indeed comparing to the capacitance value, but at high frequency, some 100,000 kilohertz, the inductance value will play Now let's move to the next example. The capacitive displacement sensor. The capacitance displacement sensor is a kind of the capacitor, the cylindrical capacitor. One of the cylinder is fixed and the other cylinder can move inside and outside from the other cylinder. And essentially, naturally, the capacitance depends on the position of the cylinder. And our task is to calculate how the capacitance depends on the position. The largest cylinder has the length of 20 millimeters and the radius of 5 millimeters, and the small cylinder has the length of 30 millimeters and the radius of 4 millimeters. Let's start QuickField and simulate this case. To calculate the capacitance, I will use the electrostatics problem. The model class is axisymmetric as I simulate the cylinders, and in my model only the upper half of the cross-section present. Let's take a look at the geometry model. I have only one block, one solid block here. This is the air block. The cylinders are made of the metal of the conductor, and there is no electrostatic field inside the conductor, so I do not assign labels to the cylinders, to the cylinder blocks, and do not build mesh. Instead, I specify the electric potential on the conductor surface. So once external cylinder has 0 electric potential, and the internal cylinder has positive electric potential. Now, what should I do to measure the capacitance? And you can move the internal cylinder in different positions. What should I do to measure the capacitance? I know the potential difference. External cylinder has 0 potential, internal cylinder has potential of 1 volt. I should simulate this case and calculate the electric charge. Or I can calculate the electric field energy. To calculate the charge, I surround one of the cylinders with contour and calculate the electric charge. Now, if I divide the electric charge by the potential difference, I will find the capacitance. And another approach is to calculate the electric field energy in the entire area. Or alternatively, you can use the capacitance wizard that will do the same. It will either calculate the charge or it will calculate the electric field energy. And the capacitance. Now I know the capacitance for the one case, one position of my sensor. 3.2 times 10 to the power of minus 12. Now let's move a bit the internal cylinder, build the mesh again, solve the problem again, and calculate the capacitance again. In previous case I have 3.3, now I have 2.0. And again the same way. But in QuickField there is the label mover utility that allows you to automate these tasks. Let me show you. I will start the label mover. Label mover can work in 3 modes: in serial analysis, in tolerance analysis, and in optimization mode. I choose the serial analysis. The next step is to specify what values I would like to measure. I would like to measure the energy stored. The stored energy. Later I will calculate the capacitance from the energy. And I should specify the step how I would like to modify my geometry model or physical properties. So I press the record steps. I would like to move the internal, let me check, yes, internal cylinder in X direction, move in X direction by 1 millimeter. So this is the first step. Move my internal cylinder by 1 millimeter to the left. And I would like automatically repeat these steps times. So now I specified the steps. I will move my internal cylinder by 1 millimeter, and for each step I will calculate the stored energy, and I calculate them in the capacitance. Now everything is ready and I can get the results. You can see this internal cylinder is moved step by step, 1 millimeter by 1 millimeter, and for each step the case is simulated and the electric field energy is calculated. Once the simulation is ready, you can see the results. Let's switch on the plot of the results. As I move the internal cylinder inside, the energy increases and the capacitance value increases. So this is the label mover that can help you to automate the simulation. Now let's move to the next example. In previous case we simulated the simple version of the electrolytic capacitor with smooth anode plates. In fact, there are perforation. The anode foil is perforated to increase the foil surface. So let's simulate this case and calculate how the perforation increases the capacitance, the surface and the capacitance of the foil. I will simulate the electrostatic problem because I would like to calculate the capacitance, and there is no electrostatic field in the conductors. The electrostatic field is concentrated in the oxide field. So I will simulate the dielectric media only, the oxide field. So let's start QuickField. I will create the new problem. I will call it pitching. This is the electrostatic problem, and the model class is the 3D extrusion. Naturally, this is the three-dimensional problem. This is neither the plane parallel nor the cylindrical. So I will use the three-dimensional simulation with QuickField. And the length units are micrometers. Now what should I do here? The three-dimensional problem, the technique that is utilized to build the three-dimensional problem is the extrusion. So I should specify, I should draw the top view of my pitching. I have the small piece of the foil on 10 by 10 micrometers only, and there is the hole inside. Now this is the top view of my three-dimensional model. And to build the three-dimensional model, I should assign the levels. Zero is the base level, and 1 micrometer is another level. 0 and 1 micrometer. Let's take a look what I have now. This is the three-dimensional object. This is the top view. And I extruded this object, this plane object, by 1 micrometer. So this is the oxide film on the surface. The oxide film thickness is 1 micrometer. And I should extrude the film here in the hole. I switch back to the two-dimensional and assign levels. 50 micrometers is the depth of the hole. Let's again take a look at three-dimensional view. And the next element I should add is the bottom of the hole. This is the bottom. I should assign levels. Now this is the bottom. This three-dimensional object represents the oxide film. I do not simulate the metal foil here, only the oxide film. Now we get the three-dimensional model. Let's assign the physical properties. The entire object is oxide. And this surface is the anode film, anode foil. Because I have the anode foil in the solid dioxide, and here and beneath I have the anode foil. So I specify on this surface, I specify the anode foil potential. And on this side and inside I have the electrolyte. This side is contacted with electrolyte, so I should specify the cathode electric potential here, here and inside at the bottom. This would be the cathode. Now we have the oxide body, we have the anode face and the cathode face. I should specify the physical properties for each object. For the oxide, I specify the electric permittivity, 10. For the anode, I specify the positive potential, 1 volt. And for the cathode, I specify 0 electric potential. Now let's simulate the case and take a look at the result. This is the electric potential distribution in the oxide film. And my task is to calculate the capacitance. So I switch to the integral calculation. I will select all objects and calculate the electric field energy. Now the capacitance is true energy divided by the square potential difference. So 2 times 3.0 72 times 10 to the minus 14 divided by the 1 and by 1. 1 is the potential difference. So this is the capacitance in faradads. This is the capacitance of the very small piece of the foil, 10 by 10 micrometers. Let's recalculate the capacitance per square meter. So I should divide this value by 10 micrometers. And again by 10 micrometers. So this is the capacitance per 1 square meter of the foil. This is 744 microfarads per square meter. And let's return to our original capacitor. In original capacitor without perforation it was only 88 microfarads per square meter, and with perforation we have 744. These are all examples for today. There are much more you can do with QuickField in simulation capacitance. If you have any question, please contact our support team and we will be glad to help you.